Now, with the tools that we've acquired for how to study a planet, let's turn our attention to the three other terrestrial planets in the solar system and see how well they fall into place with the way we have of understanding how a planet works. First thing we want to look at is the way they orbit and the way they spin. And Mercury is an interesting case. Mercury orbits very close to the Sun, so it's subject to very powerful tidal forces from the Sun. We would not be surprised to find Mercury locked into a resonance between spin and orbit, just as the Moon is locked when it orbits the Earth. It turns out things are a little bit more subtle, and the reason is that Mercury's orbit is eccentric. The following demo will explain what goes on. Mercury's eccentric orbit means that it can't quite synchronize spin and orbit because the rate at which Mercury spins cannot adjust to the rate of its angular motion around the Sun. It moves faster around the Sun when it's nearer to the Sun. It moves slower when it's farther from the Sun. The way Mercury resolves this is that tidal forces are most intense when it's closest to the Sun, so it essentially matches its rotation rate to the rate at which it moves about the Sun near perihelion when it's closest. What this means is that Mercury spins faster than it orbits, and it turns out that the ratio that it manages to do this in is a 3-to-2 ratio. In other words, Mercury completes 1.5 rotations about its axis every time it orbits the Sun once. This allows its rate of spin to match the rate at which it moves around the Sun at its nearest approach, and this is the way in which Mercury is tidally locked between rotation and spin. It orbits the Sun every 88 days. Venus orbits the Sun every 224 days. Its orbit is tilted very little, about 3 degrees to the ecliptic. The rate at which Venus spins about its axis was very hard to determine because, as we shall see, Venus is covered by a deck of clouds that makes it impossible to see the surface. Eventually, radio telescopes from Earth managed to bounce light off the two sides of Venus, use the Doppler shift of the reflected light to manage to figure out the velocity with which the sides of the planets were moving. And it turns out, surprisingly, that Mercury rotates about its axis very slowly. Once every 243 Earth days is one sidereal rotation, and the spin is essentially opposite in direction to the orbit. Mercury is almost unique among the planets in completely unique in this sense, in spinning about its axis at an effective axis tilt of 180 degrees. Its rotation is not part of the original rotation of the solar system. Quite possibly some large collision early in the days of the solar system flipped the planet over and gave it this angular momentum in the wrong direction. Mars orbits the Sun every 2 years or so. Its orbit is a little more eccentric than that of the Earth. Its day, however, is almost exactly an Earth day, 24.6 hours, and its tilt angle is 25 degrees. Its axis is tilted 25 degrees, so that seasonal variations on Mars are somewhat similar to those on Earth, although accentuated, as I said, by the increased eccentricity. It's interesting, if you want, that on Mars, there's a North Star like there is on Earth, but the direction in which Mars's axis is tilted is not the same as that on Earth. On Mars, Deneb would serve very nicely as a North Star. What do we learn by looking on the surfaces of these three planets? Well, looking at Mercury, we see evidence of cratering on the surface, so we have a relatively old surface, and we see no evidence of tectonic activity. We do see the graben and the rilles that reflect compression of the crust, the shrinking of the crust as the interior cools, but we don't see any evidence of tectonic activity. Observing the surface of Venus is difficult for reasons that will become clear shortly, but we do have radar imaging through the clouds that gives us an understanding of the topography. But again, we don't see evidence of plate tectonics in the sense in which this takes place on Earth. The entire planet seems to be one huge plate, if you wish. The crust is very strong and does not deform very easily, so we do not see the kind of features that we see on Earth. The age of the crust of Mercury is alarmingly uniform. It seems that the entire planet underwent global resurfacing maybe 400 or 600 million years ago. And the features that we do see that indicate motion in the past are indicated in these reconstructions. These are not images from the surface of Venus. We have about 3 of those. But these are reconstructions of models from three-dimensional radar measurements of the terrain. And since the terrain on Venus is extraordinarily flat, these have been enhanced in the vertical direction by a factor of about 22. And so this is a region called Ovda Regio, and it shows you these sort of compression ridges, this complicated network of compression ridges that occur when the surface is shrinking. And this other area called Gula Rift shows you these large rifts which indicate extension motion. And what we see in the background are 2 huge volcanoes. Mercury does exhibit large volcanoes. The surface of Mars, on the other hand, is heavily cratered, but only in one hemisphere. There's this great dichotomy between the north and south hemisphere, suggesting that perhaps the planet is constructed out of 2 plates, though the origins of the dichotomy are not exactly clear. And right along the boundary runs this huge canyon, the Valle Marinares, 1,500 kilometers long, dwarfs the Grand Canyon by a large margin. And this might be the fault line between 2 plates, would be reasonable. All 3 planets show evidence of volcanic activity. One is not surprised to find that all volcanoes on Mars are extinct. Mars is a small world, and as we saw on the Moon, one would imagine that Mars would cool more quickly than the others. The fact that volcanism on Mercury seems still to be active is perhaps explained by tidal friction. The strong tidal forces of the Sun are maintaining the heat in the planet. So, judging from this, we can try to understand something about the interior of the planet. So, Mercury, based on what we know about its density, has a huge core. It's uncompressed density. In other words, if you relieved gravity, it would have almost the density of iron, 5,300 kilo per meter cubed. Essentially, the density of Earth would be the density of Mercury if you relieved gravitational pressure. There is some of the core, at least, must be liquid because of features we observe in the dynamics of the planet. Also, it has, much to astronomers' surprise, missions to Mercury discovered dipolar magnetic field. So there seems to be a geodynamo at work on Mercury. That is still something that people are studying. The conjecture for how it is that Mercury came to be dominated by essentially a large core with a very thin mantle is that back in the days of heavy bombardment, Mercury underwent a rather dramatic collision, and the effect of this collision was to essentially strip the outer layers of the planet, leaving essentially an exposed core with a small covering. And so here's Mercury orbiting. Here is another protoplanet coming in, and the collision vaporizes the mantles of both planets. These are ejected, and what's left is basically an almost exposed core. This is our conjectured understanding of why it is that Mercury is so dense and is so dominated by a large core. What we know very little about the interior of Venus. We can barely see the surface of Venus. As I said, it's covered with clouds, and we can see through them with radar, but we do not have good on-the-ground measurements on Venus. We presume that the internal structure is rather similar to Earth. The density and the size are similar, but Venus does not show any geodynamic magnetic field. There are various conjectures as to why this might be. One of them, as demonstrated in this image, is that much of its core has already solidified, and therefore there's no condensation of a liquid core and no room for convection. It may be that temperatures throughout the core are uniform because resurfacing of the crust, as we saw, has now basically sealed the crust completely. There are no venting, there's no room for energy to be vented, so the entire core is heated to a uniform temperature and there's no convection currents going on. Our understanding of the interior geology of Venus is incomplete. In general, Venus is a hard planet to study. Moving on to our friend Mars. Mars has a very low density, essentially slightly higher than the density of rocks. It has a mantle that seems to be inactive. The interpretation is that its core is small. It never accumulated lots of iron. But there are traces on Mars of the existence of a geodynamo in the past. We can see the magnetic field frozen into the rocks. We'll talk about why Mars is such an underdeveloped planet as we go on with our investigation. But the similarity in many ways between Mars and Earth in terms of orbits and so on is belied by the fact that Mars is both smaller and less dense. So, for example, the gravitational field on Mars is much weaker than that on Earth. This is what we see on the interior of the planets. This is what we know about it. We can move on and talk about atmospheres. That was very important to our discussion of Earth. Mercury is an easy answer. There's not much of an atmosphere. Mercury actually is a very dark planet. Its albedo is much smaller than that of Earth. On the other hand, absent an atmosphere and with the slow rotation, you get this huge dichotomy between daytime and nighttime temperatures. 700 Kelvin on the day side, 100 Kelvin, rather cold, on the night side. And again, there are craters that are in perpetual shadow. And recently, it seems quite clear that there is substantial quantities of ice on Mercury, very close to the sun, in these shadowed craters. A calculation, if you followed our calculation for the mean surface temperature of Mercury, treating it as a black body closer to the sun, we would get 428 degrees. So the average is about right. Venus is a more interesting object. Venus has an extremely dense atmosphere. The mass of Venus's atmosphere is almost 100 times the mass of Earth's atmosphere, which means pressure on the surface is about 100 times the pressure on Earth. This corresponds to being about a mile underwater. The atmosphere is mostly carbon dioxide, so we predict a substantial greenhouse effect. There are this dense deck of clouds on the surface of Venus. This is what Venus looks like. It's covered with this dense deck of clouds. These clouds are actually sulfur dioxide. They are not water ice clouds. It turns out there's almost no water on Venus. These clouds give Venus a huge albedo, lowering its temperature. The temperature is, because of the thick atmosphere, almost uniform around everywhere on the planet at about 730 degrees. Notice that given that albedo, the fact that only 10% of the sun's radiation penetrates the clouds, our calculation would have predicted 184 degrees Kelvin as the planet's temperature. So this is a serious greenhouse effect going on. We'll talk about this. These sulfur dioxide clouds actually lead to lightning storms and rain. What rains is sulfuric acid. The surface of Venus is a very harsh environment. The Russian spacecraft Venera, which landed on Venus, survived for about 25 minutes before succumbing both to a lightning strike and to the corrosive and high-pressure atmosphere. And this makes studying the surface of Venus a very difficult task. Mars, on the other hand, goes the other way. There is a very tenuous atmosphere. The mass of Mars's atmosphere is 0.5% of the mass of Earth's atmosphere. Again, the atmosphere is primarily carbon dioxide. Presumably the oxygen generating processes happened on neither Venus nor Mars. Given Mars's albedo of 0.25 and its distance from the sun, we'd predict a temperature of 210 degrees Kelvin. In fact, again, absent a dense atmosphere, there are huge differences between day and night, and temperatures range from 308 on the equator during the day to 130 near the poles. There are these very serious seasonal changes. So it's 130 in winter at the pole and 308 in summer at the equator. Mars has large polar ice caps made, we think, primarily of water ice. Now, this is a beautiful image. There's some carbon dioxide ices in the poles, but mostly there's an active hydrosphere on Mars. Again, with such a tenuous atmosphere, you don't expect liquid water, but you do get ice and water vapor in Mars's atmosphere, and these polar ice caps sublimate. The ice evaporates in the summer to a large extent and then reforms in the winter, and we can follow the seasonal changes. the atmosphere is very dusty because the surface is dusty, and we have these huge dust storms, and there are tantalizing hints of something like water. This sequence of images from the Mars orbiter shows something that, were it on Earth, would definitely look like water flowing. You cannot possibly have actual liquid water flowing on the surface of Mars. We saw that water does not exist under such low pressures, but it may be that some heavily salted brines are able to flow either on or just below the surface. And the attempt to understand exactly how the hydrosphere of Mars operates is, of course, an area of intense interest about which we are hoping to learn from the current Curiosity rover and many Mars orbiting systems. The difference in these atmospheres, the fact that Venus has this very dense atmosphere of carbon dioxide and these extremely high temperatures, Mars has essentially no atmosphere, and in between them, Earth has an atmosphere, is something that's worth understanding. A comparative history of the atmospheres of the three terrestrial planets will probably be worth pursuing. So we have to imagine that initially all three planets would have lost hydrogen and helium, and there would have been some outgassing of carbon dioxide as rocks cooked, and there would be some water import as heavy bombardment imported ice from the outer parts of the solar system. So the initial conditions for Venus, Mars, and Earth are reasonably similar. The differences are the smaller gravity on Mars and the slightly different distance from the Sun. But note, these are differences of a factor of 2 at most. And so, despite this rather modest change, this makes a huge difference in the history, and it explains what I meant when I said there's this sensitivity to nonlinear sensitivity to details of the greenhouse effect. So on Venus, what we think happens is the water lands on the surface and the planet is hot, the CO2 is generating a greenhouse effect, the water evaporates. Because Venus is closer to the sun, the water never condenses. You never get rain. Water just evaporates right up through the atmosphere to the upper atmosphere, and there, ultraviolet light from the intense sunlight dissociates it. The hydrogen is lost to space. The oxygen binds with things like sulfur to make sulfur dioxide. Without rains, you don't build up oceans. In fact, the oceans of Venus evaporate. There's no tectonics. There's no continents building up. There's no way to recycle carbon dioxide into the rocks, which then dump it back into the magma. So the carbon dioxide atmosphere continues to build up under volcanic activity, outgassing carbon dioxide from the mantle, and there's no way to get rid of it. Once all of the water has essentially boiled away and disappeared, you have a pure carbon dioxide atmosphere, and you have a runaway greenhouse effect, which boils away the oceans, leaves a baked, parched, high-pressure, high-temperature planet. This is the story for Venus. Turn the dial a little bit down from where the Earth is and go out to Mars and start with, again, similar initial conditions. Here, water that evaporates, it's cooler out on Mars. The water does rain. This removes some of the greenhouse gases from the atmosphere. Again, Mars is not blessed with active plate tectonics. So what this means is that gas that gets trapped in rocks stays there. As rain removes carbon dioxide from the atmosphere, water that is, the planet is cool enough that water trapped on the surface becomes trapped as permafrost, we think, underneath the surface, or if it evaporates, evaporates out into space and is then dissociated by the ultraviolet light. Absent a strong magnetic field, there is no protection, and the solar wind removes the remnant of the atmosphere. In some sense, you can describe the story of Mars as a runaway icehouse effect in the same way that Venus's atmosphere is a runaway greenhouse effect. If you start too hot, you lose your oceans. There's no water, carbon dioxide builds up and the greenhouse effect takes away. You start too cold, the water freezes, does not generate liquid water to trap carbon dioxide, and again, in both cases, the absence of tectonics makes the system unstable. We are very lucky to live on a planet that splits the difference.